The steel began as tamahagane, a raw, unrefined bloom produced in a clay furnace called a tatara, where charcoal and iron sand were fed continuously over 3 days and 3 nights. The tatara was a massive construction, built from clay, mixed with rice, straw, and sand, standing nearly 1.5 meters tall and stretching several meters in length. Bellows operators worked in shifts without rest, maintaining the precise airflow that kept the interior temperature climbing toward 1500 degrees Celsius. The iron sand, satetsu, was collected from riverbeds and coastal deposits across Japan, valued for its relatively low sulfur content and its fine, consistent grain. As the charcoal burned and the iron sand melted downward through the furnace, carbon from the charcoal was absorbed into the iron at varying rates depending on where each portion of the bloom settled. The result was a single mass of steel, the tamahagane, that contained a wide range of carbon concentrations within the same bloom, from nearly pure iron at the bottom to high carbon steel approaching 1.5% carbon at the top. This variation was not a flaw. It was the raw material that made everything that followed possible. When the tatara was broken open after the smelt was complete, the master swordsmith, the tosho, examined the bloom carefully, fracturing pieces away with a hammer to read the internal grain and carbon distribution. The color of the fracture face told him what he needed to know. A bright fine-grained fracture indicated high-carbon steel, hard and capable of holding a razor edge. A darker, coarser fracture indicated lower carbon iron, tough and resistant to shattering. The tosho sorted these fragments by hand, separating them into categories that would serve different functions in the finished blade. High-carbon pieces would become the outer shell, the jacket that carried the edge. Lower carbon pieces would form the inner core, the spine that absorbed shock without fracturing. This sorting process was not mechanical or systematic in a modern sense. It was the product of decades of trained observation, a form of material science conducted entirely through visual and tactile assessment. The selected high-carbon fragments were stacked on a flat iron plate and heated in the forge until they were hot enough to be welded together by hammer blows. This initial consolidation, called tsumiwakashi, drove out the worst of the slag inclusions and fused the fragments into a single workable mass. The forge itself was a clay-lined hearth packed with charcoal, fed by bellows that the smith controlled with practiced attention, raising and lowering the temperature by adjusting the airflow. Too much oxygen and the steel would oxidize and decarburize, losing the carbon content that gave it its hardness. Too little, and the temperature would drop before the weld was complete. The smith's apprentice monitored the color of the steel in the fire, moving from black through deep red to orange, and finally to a brilliant yellow-white that signaled welding temperature, and called out when the moment was right. Once consolidated, the steel mass was drawn out into a flat bar and folded. This folding process, called orikeshi tanren, was the defining technique of Japanese swordsmithing and the source of the katana's characteristic internal structure. The bar was heated, hammered flat, scored along its length with a chisel, and folded back on itself. Then it was welded shut by hammer blows and drawn out again. Each fold doubled the number of layers within the steel. After 10 folds, the bar contained more than 1,000 distinct layers. After 15 folds, the number exceeded 30,000. The purpose of this process was not to create layers for their own sake. It was to homogenize the carbon content throughout the steel, to eliminate gross variations in hardness, and to work out the remaining slag inclusions that would otherwise create points of weakness in the finished blade. The repeated hammer work also aligned the grain of the steel along the length of the bar, improving its ability to flex without fracturing. The folding process had a critical upper limit. Beyond a certain number of folds, the carbon content of the steel began to drop as the repeated oxidation of the surface during each heating cycle burned off carbon into the atmosphere. A smith who folded too many times would end up with soft, low-carbon steel, a blade that would bend rather than hold an edge. The number of folds was therefore a calculated decision, not a formula. Different schools of swordsmithing developed their own preferred counts, and the exact number was considered proprietary knowledge passed down within each tradition. With the outer jacket steel, the kawagane, prepared through folding, the smith turned to the inner core, the shingane. This lower carbon steel was processed separately, consolidated but folded fewer times, left softer and more ductile than the jacket. The assembly of these two steels into a single billet was called tsukurikomi, and the specific configuration varied by school and by smith. In the most common arrangement, the shingane was shaped into a bar and wrapped completely by the kawagane, which was formed into a U-shaped channel around it and welded shut at the seam. The result was a composite billet with a hard outer shell encasing a tough inner core, a structure that addressed the fundamental contradiction at the heart of blade design. A blade that is hard enough to hold an edge is brittle enough to shatter under impact. A blade that is tough enough to absorb shock without fracturing is too soft to hold an edge. The laminated construction of the katana resolved this contradiction by assigning each function to a different material within the same blade. The composite billet was then forged into the rough shape of a blade, a process called tsunobe. The smith heated the billet repeatedly and worked it under the hammer, drawing it out to the approximate length and width of the finished blade while establishing the basic geometry of the cross-section. The tip, the kisaki, was formed by a specific hammer technique that compressed and shaped the steel at the end of the bar into the distinctive angled point of the Japanese blade. The tang, the nakago, which would eventually be fitted into the handle, was left thicker and less refined than the blade body, as it would not be ground or polished. The bevels that would eventually form the cutting edge were roughed in during this stage, giving the blade its characteristic wedge-shaped cross-section. By the end of the tsunobe stage, the blade was recognizable in form, but rough in surface and geometry, still several millimeters thicker than the finished weapon. The most critical stage of the entire process was the heat treatment, the yaki-ire. Before the blade entered the fire for the final time, the smith applied a clay coating, the tsuchioki, to the surface in a specific pattern. A thick layer of clay was painted over the spine of the blade and the flat faces, while a thin layer or no clay at all was left along the cutting edge. The composition of this clay mixture was one of the most closely guarded secrets in any smith's practice, a blend of clay, charcoal powder, and ground stone in proportions that each tradition developed over generations. The differential thickness of the clay coating would determine the rate at which different parts of the blade cooled during quenching, and that cooling rate would determine the final hardness of each zone. The clay-coated blade was placed in the forge and brought to a precise temperature, typically in the range of 750 to 800 degrees Celsius for high-carbon steel, judged entirely by the color of the glowing metal in the dimly lit forge. Many smiths performed the yaki-ire at night or in a darkened room so that the color of the steel was not distorted by ambient light. When the blade reached the correct temperature, the smith removed it from the fire and plunged it edge first into a trough of water. The quench was violent and immediate. The thin clay along the cutting edge allowed the steel to cool rapidly, converting it to martensite, an extremely hard crystalline structure that gave the edge its ability to take and hold a razor sharpness. The thick clay over the spine slowed the cooling rate dramatically, preventing martensitic transformation and leaving the spine in a softer, tougher pearlitic or bainitic state. The thermal shock of the quench also produced the sori, the distinctive curve of the katana. As the edge cooled faster than the spine, it contracted more rapidly, pulling the blade into its curved form. The degree of curvature was influenced by the blade's geometry, the thickness of the clay coating, and the temperature of the quenching water, variables the smith understood through experience and controlled with deliberate intent. A blade that curved too little was considered aesthetically and functionally inferior. A blade that curved too much was difficult to mount and carry. The sori that emerged from the quench was the physical signature of a correctly executed heat treatment, and an experienced eye could read the quality of the yakiire from the curve alone. The quench also produced the hamon, the visible boundary line between the hardened edge zone and the softer spine. The hamon was not a decorative element added after the fact. It was the direct visual record of the clay boundary during quenching, made permanent in the crystalline structure of the steel. The patterns within the hamon, the eniao and nioi, the fine and coarse martensitic crystals visible at the boundary, were the marks of a skilled smith who had controlled temperature and clay application with enough precision to produce a clean, defined transition. Different schools of swordsmithing were identified by the characteristic shape of their hamon: straight, gently undulating, or dramatically irregular in patterns that carried names drawn from natural forms, waves, clouds, mountain ranges, and flowers. After the yakiire, the blade was inspected carefully for warping and cracks. A blade that had warped during quenching could sometimes be straightened by careful reheating of specific zones, but a blade that had cracked was discarded entirely. The failure rate at this stage was significant even for experienced smiths, and the loss of a blade after weeks of work was accepted as part of the process. The blade was then passed to the polisher, the togishi, whose work was entirely separate from the smith's and required its own years of training. The polishing process, the togi, proceeded through a sequence of progressively finer abrasive stones, beginning with coarse stones that removed the rough surface left by the forge and established the final geometry of the blade's bevels and faces. Intermediate stones refined the surface further, removing the scratches left by each previous stone and revealing the steel's underlying grain. The finest stones, some so delicate that they were used wrapped in paper rather than held directly, brought the blade to a mirror polish on the flat faces while leaving the beveled area near the edge in a slightly contrasting finish that made the hamon visible. The togishi worked by hand, moving the blade across stationary stones with controlled pressure and precise angles, spending days or weeks on a single blade. The final polish revealed everything: the hamon, the surface grain pattern called the jihada produced by the folding process, and any flaws in the steel that the smith's work had failed to eliminate. The polished blade was then fitted with its mountings, the koshirai, a wooden handle wrapped in rayskin and silk cord, a handguard of iron or bronze, a wooden scabbard lacquered to protect the blade from moisture. These components were made by separate craftsmen: the handle wrapper, the scabbard maker, the metalworker who carved the handguard, each operating within their own tradition of specialized skill. The assembled weapon represented the combined expertise of multiple craft lineages, each contributing a component that had to meet the standards of the others. When carried by a trained swordsman, the katana performed as the sum of every decision made during its creation. The curved geometry allowed the blade to be drawn and cut in a single motion. The hard edge held its sharpness through repeated use. The tough spine absorbed the shock of blocking without fracturing. The balance point, established during forging and refined during polishing, allowed the blade to be controlled with precision at the end of a fast, powerful cut. These were not accidents of tradition. They were the accumulated solutions of generations of smiths working within a system of material science and engineering that had been refined over centuries. The katana remained the primary weapon of the Japanese warrior class for more than 500 years, surviving changes in warfare, the introduction of firearms, and the eventual abolition of the samurai class itself. The techniques developed to produce it, the differential heat treatment, the laminated steel construction, the integration of hardness and toughness in a single blade, were not superseded by a later technology so much as they were rendered unnecessary by it. The knowledge required to produce a blade of this quality still exists, carried by a small number of licensed smiths in Japan who continue to work within the same material constraints and traditional methods. Each blade they produce is the direct continuation of a process that has not fundamentally changed in 6 centuries. The tamahagane still comes from the tatara. The folds are still made by hand. The quench is still read by the color of the steel in a darkened room.